Assalamu alaikum. Today I'll be explaining the second problem in the dynamic programming set on CSES. The problem is named minimizing coins. So the problem states, consider a money system consisting of n coins. Each coin has a positive integer value. Your task is to produce a sum of money x using the available coins in such a way that the number of coins is minimal. For example, if the coins are 157 and the desired sum is 11, an optimal solution is using two coins of 5 and one coin of 1, which requires 3 coins. So we are provided with an integer n and another integer x. N is the number of coins we are provided, and x is the desired sum of money we have to make. We have to make exactly the desired sum of money, not a penny higher or lower. And then we're given n distinct coins. We have to output the minimum number of coins if we can generate the desired sum, else we have to print -1. And the coins we can have at most is 100, and the desired sum can be at most 10 to the power 6, which is a million. So time complexity and space complexity both we are looking for is around oxn, and it will pass the given time constraints. So firstly, you might think that why can't we try a greedy approach over here, being that we take the largest coin until we no longer can, then the second largest, and so on until we reach our desired amount. So let's try. First we take a coin of 7 leading to 4. Now 4 is less than 5. We can't take 5 since that would lead to us getting more money than needed. So we can't take 5 here. We'll try 1. Then we'll try another 1, and we'll take another 1, and then lastly another 1. So this we used a 7 here, a 1 here, a 1 here, a 1 here, and 1 here, which makes it 5 coins. But as the problem states, we can simply just make it using 5, 5, and 1. So this is the optimal approach, and this is where dynamic programming comes in. So this problem kind of shares similarities with the previous problem named dice combinations. So suppose the amount is the number of score you have to make, so 11. Now on 11 you have three possibilities, which is to either take a 7 or take a 5 or take a 1. After you take 7 from 11, you're left with 4, and now you have to check the case for 4. After taking 5, you're left with 6, and after taking 1, you're left with 10. So over here I can't take 7 again because 7 is larger than 4. Similarly, I can take 5 because of the same reason. So the only possibility I have here is taking 1. Now over here I have two possibilities, either take a 5 or take a 1. This will leave me 1, and this will leave me with 5. Now in both cases you can see that we can reach 0 over here and fulfill our goal. Over here I can take 1, leaving me with 0. Over here I can take 5 or I can take 1, both this leaving me with 0, this leaving me with 4. Okay, now here you can see that this 4 case and this 4 case is redundant. So this is where dynamic programming comes in. If we just simply did it recursively, we'd have to recalculate multiple states again and again, but using dynamic programming here saves us time as well as makes the work easier for us. So the nature of this problem is that for higher totals we might require the sum, we might require the output of the calculation of lower totals. So for 11 you can see that we used 4, 5, 3, 6, 10, and so on to make up 11. So we'll have to calculate it in a way that every required thing is pre-calculated. So yes, this is how dynamic programming will work here. We can imagine this 751 as if I compare it to the previous problem, you can imagine the number of coins as being the face of the die, and this is our desired goal, 11. So yes, this is how dynamic programming works here, and I'll now code it up. uh, this is integer int n for the global array, and this is a coins array. I'll resize it and as well as take an input int x, and then I take an n and x. Also, I didn't discuss the -1 approach, the -1 possibility. So suppose I have 2 coins and the total I have to make is 3, and the coins start from, I have 1, I have a 4, and I have a 9. So I can't make up 3 using any of these coins since they are both larger. So here I'll take in the input of x, both n and x. Now since I pre-declared the coins array, I'll just make it coins equals to vector int of n. Then I'll take an input for the coins. And then I'll do int ans equals to minimize of x if answer greater than or equal to infinite. So the reason I'm using the infinite here is, on the worst case you can see that we're given with a single coin of the value 1, and my total is 10 to the power 6. So I'll have to take 10 to the power 6 coins, so that's the worst case I have. So I'll just set the infinite value a bit higher than this. I can also use int max, but I'll just avoid it to avoid overflow. Now I'll write the minimize function over here. It receives integer x, and then I'll minimize it. So firstly, if the current coin I'm taking makes it go to negative, so I'm taking more than I require, so that's obviously impossible. So I'll return the identity element over here being infinite. Since we're minimizing, I'll return a higher value so it doesn't affect my answer. If x equals to 0, it means I've hit my base case, so I'll just return 0 over here. Since it takes 0 coins to make 0, this is my base case. I'll be using it for the iterative DP as well. Also, I'll have to fill up the DP array with -1 so I can memorize. And if it's already pre-calculated, then I can just return over here. So firstly my answer will be infinite, and then I'll try to take every coin and see where it takes me. This will be n. So this is like if I have already pre-calculated, and suppose one thing gives me a bigger answer. So this is for minimizing, so I'll just choose the value, choose the operation which gives me the minimum answer. So I'll use the coin over here, so I'll do f x minus coin I. So suppose I'm at 7 and I'm choosing the coin 5, so this will give me f2 plus 1 since I'm using a coin over here, and then at the end I can just return after, this will give me the answer for, like, suppose we start at 11. If this takes the coin 5, it will go over here. Then the function like recursively calls 6, then it will call 1 if I take another 5, and then it will call 0. So the total number of coins becomes 3. I'll minimize, this is minimize, and then I'll just return over here, and I think this looks good. I'll run it. Okay, this is coins, and this works, so I'll try submitting it. So this works. Now I'll do the iterative approach. So over here, same, I'll take in the input. I'll just copy it from there. Okay, now since we have to perform the work in our DP array, I'll set it to infinite, since initially the possibilities of all coins of all sums is infinite. Then my base case is it takes 0 coins to make 0, so I'll set it up over here, and then I'll calculate from 1 all the way to x, that to make this certain sum, to make the sum I, the it will be dp of I equals to minimum coins to make sum I. So for every I, I'll calculate so I can use it in the future. For int auto coins, now I have to handle the negative case here. So if I'm taking coin more than I require, I'll set up a if condition so I don't take that coin. So if I minus coin, if I minus coin less than 0, continue, and dp of I equals to minimum dp of I, or if I take this coin, then dp of I minus coin plus 1, and then I do the same thing, int ans equals to dp of x, if ans greater than or equal to inf cout minus 1 handle, else cout ans handle. Let's see if this works. It does, so I'll submit this as well. Yes, so there you go, this works as well. And yes, this was fairly a straightforward dynamic programming problem. It shared a few similarities with dice combinations, so wasn't that difficult. I hope everyone understood it, and I'll be posting coin combinations once soon. If you had any confusion in anything, you can let me know in the comments and ask me, and I'll try to help as much as I can. Thank you for watching and take care. Allah Hafiz.